Hello everyone, my name is Ray Bosman. I'm a senior developer in Durban. I work for a company called Derivco, and that affords me to do some pretty cool things. Today, one of the things I'm going to talk to you about is factorization machines with an emphasis on Simon Funk's FunkMF, which him and his team used in 2006 to attack the Netflix problem. They came third place, but the method was quite interesting, and it's kind of you can find it in a lot of modern recommendation systems if you look around. You would use this approach if you're trying to impute missing values. So the most intuitive one is, think of image data with missing pixels. Anywhere you've got pairwise interactions. In the commercial sense, it would be customers and services. So if you're Takealot or Amazon, you want to find products that people would use, this is an approach you could potentially use to evolve that kind of system. So at the core of it, excuse me, at the core of it you have matrix P and Q, where if you smash them together you get matrix R, or a synthetic matrix as I call it. Why would you be interested in a fake or synthetic matrix? Well, if that matrix has an uncanny resemblance to your data, you could potentially borrow those values and put them into your empty cells, and therefore recommend the highest scoring recommendations back to the user. So on the left is my data with missing values, and on the right is after the imputation, and I would therefore recommend the highest scoring ratings imputed. The way that these methods of these values are found in matrix P and Q is gradient descent. So that's key of what Simon Funk did. They've hunted down these initialized coefficients using gradient descent, which you can find you do find in neural networks, and then try to reduce the distance between your synthetic matrix and your real matrix. So the intuitive example is this image where I've corrupted 40% of the pixels. I generate a synthetic using the same approach, and then I take the synthetic and I put the values back into the corrupted image, thereby restoring it. So if I stop the algorithm at each or an X number of steps and peek into where it's progressed to, this is that progression. So initially you can see it starts with very few features, but after a couple of increments, the details are captured by the factors in matrix P and Q, imputed back into the original corrupted image. When I learned about this method, I tried to find something in R. I couldn't find anything. I did find something subsequently, but instead of looking, I went and tried to write my own. So I found a tutorial, little Python tutorial, very simple article, which was very effective, and then rewrote everything in R. I added parallelism. I added its ability to handle images, and the guy who wrote that is Albert A. Young, a brilliant computer scientist and machine learning engineer in Hong Kong. And so a very small key piece of the puzzle is inside this R code that has been transposed. You can find this R code on GitHub. Look for github.com/sledgehardy. All the images that you saw in this talk were all generated using this R code. It's a one-trick pony. It's a big God object, and you just pass in parameters, run it, and it'll pop out a corrected image for you. You can find me on LinkedIn at Ray-Bosman, and my email is curryroad@gmail.com. Thank you very much.